Hello, grade 12s. In this lesson, we're going to go over average and instantaneous rates of reaction. So we are concluding almost our discussion on enthalpy and thermal chemistry. We're going to get into now kinetics of chemistry. It's a pretty short segment or part of this unit, but we're going to start now. So chemical kinetics is just the study of ways that chemical reactions can go faster and slower. So that would involve then the need to figure out. Let's get a pen going. The need to figure out the rate of a reaction, and there are a few different ways that this can be determined. Right. Um, First, the consumption of reactants to products can be measured in different ways. Also, the increased constants of reactants to products, also the increased concentration, right, of products can be measured in different ways to figure out the rate of a reaction, right? So that means if a reactant is then being if its concentration is should be decreasing, right? Naturally, if the reaction is moving in the forward direction, that's one way we can measure rate of reaction, or if the products are increasing at a certain rate, it's another way we can measure the rate of a reaction. Okay, so these are the ways, different ways. Depending on the reaction, you can measure the amount of gas produced. So if the reaction is moving in a forward direction, we'll talk more about forward or backward directions in our next unit. But if the reaction is moving in the forward direction, you have gases produced at a certain rate per unit time, usually seconds, minutes. Then you can measure that gas production by looking at it as a volume change. Also, if it's an open system, you can measure the mass lost, right? That would be the consumption of reactants as well, or in this case, using indicators, you can measure pH differences in pH at certain times. You can use a pH probe for that. You can measure differences in electrical conductivity. So there are different ways to measure the rates of a reaction. Okay, let's get into some math. So the average rate of a reaction is not too much of a foreign concept here because it is just an average rate of reaction. So it's a difference between 2 points in time 2 and time 1, measuring then the concentration of a general compound. Let's just say it's A, of reactant A. Will be general for now and just say A. So concentration of A at time 2 minus concentration of that same compound at time 1 initially. Okay, that means we see a concentration change. So delta concentration of A per unit time per second. So the concentration we know is measured in moles per liter. Now, if that is being divided or per second, we'll just say moles per liter per second. Right, so these are our units. Okay. So again, there are two ways, we alluded to this before, there are two ways we can measure a rate of a reactant. We can say if the reaction is going from A to B, reactant to product, how fast a reactant disappears is a concentration change per unit time, or how fast a product appears is rate of concentration change. Let me rephrase that, concentration of B product per unit time, so the rate of change of B. Now, something to point out here is that there is a negative sign for the disappearance, right? Disappearance, negative sign, or decreased concentration per unit time of reactant A. There is a positive sign here for the production or appearance of product B. All right, so in the next example, we're going to consider reactants A to B. We're going to measure the average rate of change at different points in time given different concentrations. All right, so here we're looking at this reaction, production of an alcohol from an alkyl halide here. Back to our organic chemistry unit for just a moment there. Don't worry, we'll stop right now and get into some math, some pretty simple math. So here we're going to calculate the average rate of disappearance. Now the wording in these questions can be tricky, but just pay attention to it and it should be fine. It says disappearance of chlorobutane. Okay, so between 0 seconds and 50 seconds. So this is our time 2 is 50 seconds. We'll say time 2. And time 1, our initial time is 0. So we have to measure this. Rather, it is measured here, we're going to then calculate the difference between these two times and calculate its rate of change of chlorobutane. So let's put that together. All right, so rate, okay, you would write C4H9Cl here, but trying to save some time. Let's see, rate is at time to that value, so let's write that down, 0.0905. Big M stands for molarity or moles per liter, minus 0.100 moles per liter, and we're going to divide that by time 2 minus time 1. So 50 seconds minus 0.0 seconds. Okay, work out the math, and we get negative 1.9, right, times 10 to the negative 4 moles per liter per second. Okay, now it's asking us for the disappearance. What is the average rate of disappearance of chlorobutane? This is the rate of change. Notice the difference in language. I said change, right? The question though was asking for the rate of disappearance. That means in our therefore statement, I'm going to have to write that over here just for some space. The rate of disappearance. Let's go ahead and write that down. Sorry, my pen's lagging a bit. That's a disappearance. Is I'm going to emphasize that by writing a positive 1.9 times 10 to the negative 4 moles per liter per second, right? Because it already implies a loss in concentration by saying disappearance, you don't need to put that negative, so be careful with that. All right, next, B, we're now comparing to other times, or the points we have between 50 seconds and 100. So that means I'm going to exit presentation mode, and let's erase just some of this here. Okay, and back to my pen. All right, so between 150 seconds, 100 and here is 50. All right, so rate, okay, at 0.0820, big M minus, I'm going to make myself some room here, 0.0905, big M, I'll put brackets around that so keep us a bit organized here. Okay, minus 100 seconds, sorry, not minus, divided by 100 seconds minus 50 seconds. And we get negative 1.7 times 10 to the negative 4 moles per liter per second. And again, because it says disappearance, change here, because it says disappearance, I'm not going to rewrite a whole statement here, but this sign would have to actually be positive. So we would say the rate of disappearance is positive 1.7 times 10 to the negative 4 for B. Okay. All right. So your average is then, it's just really just a slope, right, between 2 points. So this is a graphed version. So if we graph these points here, we get this rate of change for this reactant, for chlorobutane, right, over time in seconds. Between two different points appears to be 300 roughly, 300 and 500. If we draw a line to connect those points, what we're really looking at is a change in y over change in x, which is slope. Right, so that is an average rate of change between 2 points. which is called right. We're using this secant line or slope again to figure out that difference between those 2 points. Okay, slowly progressing now onto something that you're probably studying right now is an instantaneous rates of change. Right, and if you remember from your calculus class, it's that line is not called a secant line. That line is called a tangent line. Right, most reactions don't follow a perfectly um, linear trend behavior in their reaction rates between 2 points. We can see it's not linear. So a secant line can only tell us so much. It will just tell us what's happening on average between 2 points, but if we need to find rate of change at a particular point, that secant line is not going to help us. All right. You will not be responsible for any math, any calculus math at all, but just know the difference between an average rate of change versus an instantaneous rate of change. I should point the last point out, and this really is the main difference. The rate of change of a chemical reaction at a single point in time, that is the instantaneous rate. So instead of between 2 points, what is happening, not between 2 points, what is exactly happening at, let's say, 60 seconds? What is the rate of change of your reactant, or whatever this is measuring here, of your reactant A, let's say, at exactly that point? And what calculus does is well, initially you're going to be studying this through first principles. What it will do is it will attempt to approach this line. So let's calculate a secant line between those 2 points, and then between these 2 points, and then between these 2 points, and then really, really close together between these 2 points until there is very little space between them, and that would then become 1 point, your tangent line. Okay, where you can then draw a line at just that point. So in other words, a slope, but just at 1 point. Okay, or the slope called the slope of the tangent. Now, this reminds me a bit about calculus. For those of you studying this, you'll be reminded of solving for your tangent line using first principles. A plus H minus F at A over H, right? If you're not taking calculus and this doesn't interest you, it interests me. But if it doesn't interest you, don't worry. You're not going to be tested on that. I'm not going to ask you to find the slope of a tangent line at all. But you can see where this can extend into a whole other field of math that we haven't done in this course at all. We really only get to about grade 10 or grade 11 math in our next unit. Okay. As a prelude into our next lesson, just want to say that a stoichiometric relationship, right? So here we're looking at stoichiometry, looking at balance equations and mole ratios. We can use mole ratios of a balanced equation to make predictions about the reaction rates. Right? That tends to make sense, right? If you have, let's say, 2A plus B produces 3C, well, these coefficients, these mole ratios, we know are related to each other. 2 to 1 to 3 in this case, they're likely going to change in a similar ratio. So that's all I'm saying here, and we'll continue this in our next lesson. All right. So here's your homework. Let me know if you have any questions. I hope this helped.